So first of all, on your left screen, I have the diagram and formulas that Bengt looked at earlier. And I just want to take a moment to go back to the Formula 1 and just talk a little bit about it. Now, we know what Y is. That's the outcome. So you've measured your outcome repeatedly, and you want to do a growth model. So you know what that is. We're estimating eta sub 0. That's the intercept growth factor. And we're going to try to always refer to it as the intercept growth factor to make it clear. Eta sub 1 is the slope growth factor. We're going to be estimating that as part of our model. And I'm just going to skip x for a moment. And then we have our residual, which is also estimated. So what we need to talk about as a first step is x sub t, and what Bengt referred to as the time score. So our first job is to figure out, okay, how do we come up with these time score values so that we can put them in the growth model so we can estimate it. As Bengt mentioned earlier, for eta 0, there's an invisible 1. So all of the paths from eta 0 to the 4 outcomes, y1, y2, y3, and y4, are fixed to 1. So now the question is, what about the time scores? What do we do? So let's first talk about the simplest model, the linear growth model. So we're assuming that the development is a straight line with some sort of a slope. So there is no nonlinearity. It's just a straight line where the change is the same along that line between values of x. So for a 1-unit change of x from 1 to 2, 2 to 3, or 3 to 4, you have the same change in y. So it's a linear model. So how do we come up with the time scores for the 4 time points, 1, 2, 3, 4, that we show on the axis? Well, basically, we want one of the time scores to be 0, because this defines the intercept growth factor, and we'll be talking about that. And if you choose the first time point, that would be defining the intercept growth factor as initial status. If you fix the 0 at the last time point, you would be defining it as final status. So right here I'm showing you equidistant time scores. So what we mean by equidistant is that your outcome was measured with the same distance between the measurements. So in one example we're going to look at, we have grades 7, 8, 9, and 10. So there was a 1-year difference. And now we're also going to be talking about non-equidistant. But if we have equidistant time point, our outcome was measured at the same time intervals, then we would have equidistant time scores. So if we start with 0, if we want initial status, then we would just have 0, 1, 2, and 3. So it's very simple. And the scale, you could have 0, 0.1, 0.2, or 0.3. The scale doesn't really matter other than if you choose a very large scale, like 0, 100, 200, 300, these do get involved as starting values for the model estimation, and the very large values could cause convergence problems. So unless you have a reason, I think sticking to 0, 1, 2, and 3 probably makes more sense. Let me come over here now. So we need so with the linear growth model, we need 2 latent variables to describe it, eta 0 and eta sub 1. So, and that's the intercept and slope growth factors. Now, let's say that you have non-equidistant time scores. So let's say that you had a grant and you were happily measuring times 1 and times 2 here, and then all of a sudden your funding dried up for 2 years. Not good, and you're worried, what do you do? So, but then you're lucky and you get refunded and you get to measure in year 5, 6, and 7. And you think, oh no, missing data, oh, it's going to be really messy. Well, with non-equidistant time scores, missing data isn't an issue. All you need to do is reflect the fact that you didn't measure at times 3 and time 4 in your time scores. So let's say time 1 is 0 and time 2 is 1. So 0, 1. You would have had 3 would be 2 and 4 would have been 3. Just skip those and then just have time scores 4 for 5, 5 for 6, and 6 for 7. So the non-equidistant time scores take into account that you were not able to measure each year. You may also have missing data to be concerned with, but at least you don't have to be concerned about it for this reason. So you have your time score for your slope growth factor would be 0, 1, 4, 5, and 6. And always for eta sub 0, the time scores are always fixed to 1. So let's see what we have next here. All right, so just to take the formula that Bengt showed you earlier and that we've been looking at, and let's just fill in the values and see what happens. So in our example, our times are 1, 2, 3, and 4, and x sub t is 0, 1, 2, and 3. So at time 1, eta sub 1 falls out, and y is just equal to the intercept growth factor plus a residual. And at time 2, the time score here for eta sub 1 is 1. At time 3, it's 2. And at time 4, it's 3. So this is how these time scores come into the formulas. And then let's talk about these, because remember now, the intercept and slope growth factors are variables. We're doing random effect modeling. They're variables, and that means they're going to have means, variances, and covariances. So what is eta sub 0? It's sometimes, if we fix the time score at 0, it's going to be initial status or level. And it's just a systematic part of the variation in the outcome variable at the time point where the time score is 0. So the 0 time score defines the intercept growth factor. And we're going to see when we talk about centering how we can change that and therefore understand what explains maybe what covariates can be used to explain initial or final status. Or you can change it and have a different set of covariates at each time point that has the time score of 0. So then we have our slope growth factor, and that's the growth rate or trend. So it's the systematic part of the increase in the outcome variable for a 1-unit change in the time score. So we're in regression. The time score is x. For a 1-unit change in x, y changes so much. So everything we do is just based on simple linear regression, and it's just like you saw in your first simplest statistics class. So for a 1-unit change in the time score, the outcome changes for the slope of eta sub I. And as I put here, time scores are determined by the growth curve shape. Now we're talking linear, and we're going to be talking about quadratic models. We're going to see models where you can estimate time scores. We're going to see a piecewise growth model where you can show the growth in 2 different parts. Like let's say maybe you have an initial increase, and then the next part is an increase but at a slower rate. And you can use a piecewise model for that. Let me put this over here. Okay, now I think it's important for us to think about what the parameters of this model are and what they actually mean. So I've broken this up. So here's the parameters for the intercept growth factor, and then for the slope growth factor. So we're going to talk about the parameters for each and what they mean. So the intercept growth factor has a mean and a variance because it's a random effect. And the mean is just the average of the outcome over individuals at the time point that has the time score of 0. So most of the time we're thinking initial status that the first time point has time score of 0. But that doesn't have to be that way. So it's just the average of all of the individuals' outcomes at the time point with a time score of 0. And when the first time score is 0, it's called often initial status, as I already said, and if the last time point, final status. And then the intercept growth factor has a variance. And it's the variance. So each person has a value on the intercept growth factor, and the variance is just the average of those. So if you have a lot of variability, the variance is going to be large. If you have very little, the variance is going to be small. This is how you come by using this model to understand individual variation in the growth process. If everybody grows starts out at the same place and grows at the same rate, then you're not going to have a lot of variation. It's going to be very small. It might actually be a fixed effect rather than a random effect parameter. You might think of it that way if the variance is really small. But what's important is to remember that these are random effects, so they have means and variances. And we're going to be talking about other random effect parameters as the days go by, and to have that solidly down in your mind that a fixed effect parameter just has a point value, a random effect parameter has a mean and a variance. Just to keep that in mind for yourself. So when you're looking at the output, if you've estimated a random slope, for example, you want to know where's its mean and where's its variance. So the slope growth factor also has a mean and a variance. And the mean is just the average growth over individuals. So everybody has their own growth rate, but the mean of this slope growth factor is the average. And the variance is just the variance of the growth. And once again, if the variance is large, that means that people grow at different rates. If it's very small, they grow at similar rates. And that's what we're trying to understand from this type of modeling. And then we can have a covariance with the intercept. So that's the relationship between the intercept growth factor and the slope growth factor. And let's say it's positive. So that would mean that as people who start out high grow faster, people who start out low grow slower. So that's also important to look at because you want to understand what is happening in your process that you're interested in studying. And you want to be able to explain why that's happening. And we'll be also looking at models that will help us explain that by letting us add covariates to understand what what explains the variability in both the intercept and the slope growth factors. So where people start and how they grow. So those are the questions that we're going to be trying to answer. Okay, so let me put this one here and this one over here. So here's the model that we're going to be looking at. You've seen this before. So here's our outcome, y1, y2, y3, y4, eta sub 0, eta sub 1. And somebody asked a good question during break about why sometimes we only have 3 arrows pointing to the outcomes 2, 3, and 4 in these diagrams, and sometimes we have one pointing to y1. And it's just that when the first time score is 0, we often leave this out. Sometimes we don't. I think we didn't agree with that, and we never came to an agreement. So if I do it, the arrow's there. If he does it, the arrow's not there. Doesn't mean anything. Anyway, so here are our outcomes, and what are these arrows pointing into each of the outcomes? Well, these are our residuals, the epsilons. We can estimate those, and as was mentioned during the question and answer session, if you do the wide format, you can estimate a different residual at each time point, whereas if you do the long format, these are held equal. So that's one of the advantages of this type of model. And what else here? We have the covariance between the two intercept and slope growth factors. And let's talk about this model. We mentioned that 4 is probably the minimum outcomes that we would measurement times that we would recommend. And we have a reason for this, and I'm going to tell you that reason right now. So let's think about it. First of all, let's think about how many free parameters are in the H1 model, or the unrestricted model. So we have 4 variables, so we're going to have 4 means and 10 variances and covariances. And how about the H0 model, our growth model we're interested in? How many parameters will we have there? Well, we have the means of the intercept and growth factors, so that's 2. And they also have variances. That's 2 more, and a covariance. So right there you have 5 parameters. And then you have residual variances for each of the outcomes up here. So that's 4 more. So that's 9 parameters, and 14 minus 9 is 5. So we have 5 degrees of freedom. And why is that important to us? Well, we may need to modify the model. It may not fit. We may need to free a time score. We may want to add a residual covariance up here. So this gives us 5 degrees of freedom to modify the model to fit better. However, if we have less outcomes, we're going to have less flexibility. And I'll talk a little bit about that in a minute. So what are the sources of Misfit that we might want to use those 5 degrees of freedom for? Well, we could free time scores for the slope growth factor. So that would be these 3 paths. We may be able to free one of those. Or we could add residual covariances. So that would be arrows between epsilon 1 and 2, 2 and 3, 3 and 4, something like that. We might need to add those. Other sources could be the outcome variable intercepts, which are fixed to 0 in this model, or the loadings for the intercept growth factor, which are fixed to 1. Now, the first 2 are recommended. The last 2 are not recommended because the last 2 are part of the parameterization of the growth model. So the intercepts of the outcome variables are fixed to 0. And the factor loadings for the slope growth factor are fixed to 1. That's part of what makes it a random, of the intercept growth factor are fixed to 1. That's part of what makes it a random effects growth model. So you wouldn't want to change those, because if you did, you might have an interesting model, but how to interpret it would be difficult. So if you're going to make modifications, it would be freeing the time scores or adding residual covariances to that model. Now let's take a minute to look at the same type of counting of degrees of freedom if we have 3 outcomes, if we've repeatedly measured our outcome on 3 occasions. In our H1 model, we have then 3 means and 6 variances and covariances, which is going to be a total of 9. Now, we still have to estimate, so basically that would be eliminating Y4 from this model. So we still have 2 growth factors, the intercept growth factor and the slope growth factor. So we still have to estimate their means. We still have to estimate their variances and covariance. So that's 5 parameters. Then if we have 3 residual variances, 1, 2, 3, that is a total of 8, which only gives us 1 degree of freedom. So if we freed that, then we would have a just identified model and we couldn't test model fit. Now, one could consider doing what they do in the long format of the growth model and hold the residual variance is equal. But it's nice to know that they're equal before you hold them to be equal, and you can't test that. I guess you could test that, and then if you see they're equal, hold them equal. But in our experience, when we've been working with these models, the residual variances aren't equal. I mean, that is a somewhat restrictive assumption. And one thing I didn't talk about on the slide with the 4 is the fixed parameters in the H0 growth model, so the model that we're interested in. I've said this, but let me state it again. So the intercepts of the outcome variables are fixed at 0. The loadings for the intercept growth factors at 1 and the loadings for the slope growth factors are fixed at the time scores for the simple linear model, and the residual covariances are 0 as the default, but you could add those to modify the model. So basically, with 2 time points, you can estimate an intercept-only model. So you would be able to estimate the intercept growth factor, but not the slope, because you wouldn't have enough information to estimate that model. So if you're writing a grant or in a situation where you can influence how data are going to be collected in a longitudinal setting, I think that you could use this type of an argument to say that a minimum of 4 measurement occasions is probably warranted if you really want to get much out of the data once you have it collected. So we're going to skip the next 2 slides and just talk briefly about this page. As far as model estimation in Mplus, we have maximum likelihood estimation available, and this is available not only for continuous outcomes, but also for categorical outcomes, which is, sometimes people think, oh, you can't do maximum likelihood estimation with categorical outcomes, but you can. It just may require numerical integration, which can be computationally heavy, but you can do it. So we have regular maximum likelihood and non-normality robust maximum likelihood. We also have, for multi-level models, quasi-maximum likelihood, which is for balanced data, maximum likelihood, and for unbalanced data, a quasi-maximum likelihood. We have weighted least squares, and this is for categorical outcomes or for a combination of continuous and categorical outcomes. And then for missing data, we have maximum likelihood with the EM algorithm. For model testing, we give chi-square, robust chi-square, RMSEA, other fit measures like CFI, TLI, when they're available. And we'll be discussing models for which they're not available in the Tuesday and Wednesday, and we'll be talking to you about why they're not available. That's always a big question. We can also get model modification indices, so either the drop in chi-square or the change in the parameter estimate value, if that parameter is free. And we have factor scores available, and we use the regression method, which is also referred to as empirical Bayes. So we have a lot of, for example, Fourier intercept and slope growth factors. They're factors, so you can get factor scores for them. The factor scores being the individual's values for the intercept and the slope. So that's available as part of these growth models. And the model and modification indices are helpful also to see how you might want to modify your model. We recommend not making modifications that don't make sense, not just making all possible. We give you every modification index for every fixed parameter in your model or every parameter that's held equal. So we don't make a decision about whether they make sense. You need to make that decision when you look at them and have a rationale for freeing a parameter that's fixed. So also, I'm going to look at slide 53, although slide 52 is also the same, but I'll just do this in words. We have two different parameterizations of the growth model that we use in Mplus for different types of models. They're identical. You would get the same results if you did either one with the same data, but we recommend for continuous outcomes, which we're talking about today, that the parameterization where the outcome variable intercepts are fixed at 0 be used, and the growth factor means are free to be estimated. However, when categorical outcomes are used, or multiple indicator growth model, so that would be a growth model where the growth is on the factors, you have multiple indicators of each factor, then we recommend that the intercepts, or in the case of categorical outcomes, the thresholds be constrained to be equal, and that the intercept growth factor mean be fixed to 0, and the slope growth factor mean be estimated. Now, the reason we do this with multiple indicator and categorical outcomes is that for polytomous categorical outcomes, you would have to fix, it would be a very strong, it would be more restrictive than necessary if we fixed all the thresholds for an ordinal variable to 0, for example, when one could hold threshold 1 equal across time, all the threshold 1s, all the threshold 2s equal across time, all the thresholds 3 equal across time. So it's a more flexible model for that. In the binary case, if you fix it to 0, or if you hold them equal across time, you're going to get the exact same results. What you would normally find as the mean of the intercept growth factor, that parameter value you will find as the threshold value held equal. So it's just reparameterizing the model, putting something in a different place. It doesn't change the model fit. You'll get the exact same chi-square value. And if you are experimenting with this just to show yourself how it works and to understand it better, which I always think is a good idea, if you don't get the same thing, then you should email me at support so I can help you or show you what's going on. But anyway, so you're going to see in the user's guide, and you're going to see in examples that we do, that we will be using these different parameterizations. So we want to just put this out now. When we get to the models that use the different parameterizations, we'll go over that with you. Okay, so now we're going to do our first example. I think we know everything we need to know now to do that. So here's just a little summary of steps that you might consider taking when you're doing the growth model. And it's very important to do this preliminary work, because if you just say, okay, here's my data, I think I'm reading it right, let me just estimate this growth model, and it doesn't work, it's really hard to start picking it apart from that place. It's better to come from the beginning and do your preliminary work and then know that you're at least estimating a growth model that may be feasible for the data. So anyway, first of all, you want to do your preliminary descriptive work by looking at the data, as Banks showed earlier, both the means of your outcome over time and also individual plots. Now, you can really only do these for continuous outcomes, because for categorical, it doesn't show you anything that makes sense. But you can use our plot command to look at individual observed curves for people, and you can get an idea about what they look like. Do they look linear? Do they look quadratic? Does it look like it goes up and then straightens out? Just to get a feel. The mean will give you, looking at the means will also give you a feel, but looking at the individual curves will tell you how much deviation there is, and may point to the idea that you might need to do mixture modeling, where you look at unobserved classes of individuals who may have different growth trajectories. You can also determine the shape of the curve from theory. You may have theory that says how development is supposed to occur, and you might use that. You also want to look at the change in variance across time, and you can look at that in your sample statistics. You want to see the variances increasing across time, not decreasing. And I always recommend fitting the model without covariates as a first step. I think from what I see sometimes on support, I think people put everything into the model at the same time to estimate it. But basically, you want to have a well-fitting growth model. You really don't want to explain the variability of an intercept and slope growth factor from a poor-fitting model. That's sort of adding insult to injury. So at least get your growth model to be feasible and reasonable and to fit the data well before you add your covariates. And when you add the covariates, this should not make a huge change in your model fit, for example. If it does, it may point out that you may need a direct effect from the covariate to the outcome, and we'll be talking about this. But you want to do these steps all very carefully and thoughtfully, and so that at the end you feel confident in what you're interpreting. Because if a model doesn't fit the data, then interpreting the results is not a valid thing to do, because it makes no sense to interpret results of a poor-fitting model. So you want to take your time and make sure you get a really well-fitting growth curve before you go on to add the covariates. So the first example we're going to look at is from the LSAY data that Bengt talked to you about earlier. And we're going to look at math achievement in grades 7, 8, 9, and 10. And these are the same plots that he showed you earlier. So we see the mean growth curve, and it's obviously not perfectly linear. And if we look at these curves, we can see that some look similar to the means, but there are some that are different. This one dips down and then goes up and over, and another one goes up a lot between 8 and 9. But in looking at the means, you could consider that a good place to start would be a linear model. That's often a good place to start your analysis. And then look at model modification indices to help you determine how you might change the model to get better fit. So one thing that you can use in Mplus is the type equals basic analysis. This gives you sample statistics, and so then that would be how you would get the means to look at in your preliminary descriptive work. And I think everybody here has everybody here been to another Mplus training course, or how many haven't? Oh, a lot haven't. Okay, so let me talk a little bit about the Mplus language. I don't want to bore people if they already know it. So basically, the Mplus language has 9, I think, commands. And the commands like title, data, variable, analysis, and plot, they all end with a colon. And each command then has several options. And for example, the data command has the file option. That's used to name the data set. So that says file is LSAY.dat, so Mplus goes and looks for LSAY.dat. Another option is the format statement if your data are being read with a fixed format. If not, you don't need this statement. If your data is free format, you just give the name of the data set. The variable command gives the names of the variables in the data set, and it has several other options like use observations here or use variables. Use observations is used to select a subset of the observations, and use variables is used to select a subset of the variables. The analysis command tells what type of analysis a person wants to do. You can select different estimators. If you don't want to use the default estimator, that's where the analysis command has the estimator option, where you can change that. So here I'm saying type equals basic, because I just want to get some general descriptive statistics. And in plot, I'm saying type equals plot 1, because that's going to give you those individual observed curves that you can go through. You can randomly select 50, for example, from your data set to look at, or you can take it in groups of 10, first 10, second 10. So it's quite a nice feature, actually, to be able to look at this. So this is the first example, then, of the Mplus language. And this is, on the left screen here, this is what you would get from the type equals basic. So you will get your means and your variances and covariances and correlations. So you can see from the means that, just what you saw in the plot, that it's not equidistant between the mean of mass 7 and 8, 8, 9, 9, and 10. So it's not exactly linear. You can see your variances are increasing. Sometimes variances decrease, and that's not a problem. But sometimes, if you're having convergence problems, that's something you might want to look back at just to see whether that might be causing a problem for you. So basically, you take a look at this. You go to the plot command. When you use the plot command on the menu bar, you have the graphics results. You just click down, and it shows you what plots are available. And then you just bring the plots up, and then you can start looking at the individual observed plots. So here's a path diagram that now is not generic, but is specific to our example. So we have outcomes Math 7, Math 8, Math 9, and Math 10. We're going to name our intercept growth factor I and our slope growth factor S. And this is the model we're going to estimate. We're going to estimate the residual variances. They're different for each time point. And we're going to estimate the covariance between I and S. All of the time scores are going to be fixed. So this is just what we've been looking at, but the names are changed to reflect the data that we're looking at. And here's the input for this path diagram on your right screen. So this is a linear growth model without covariates. And let's take a look at the model command. Now I'm showing, in Mplus we have a special growth language now, which makes it a lot easier so you don't forget things when you're doing it, which I used to always do, which is why I decided we needed a special growth language. But what we're showing in the model command here is not the growth language. That's shown down here, alternative language. Instead, I'm showing it using the factor analysis by option. So by is what's used to define latent factors in Mplus, latent variables that are continuous or factors. So what we're saying here is I by Math 7, and you can use a dash in Mplus if you have a list of variables. So Math 7 dash Math 10 refers to Math 7 to Math 10, which is up here, Math 7, Math 8, Math 9, and Math 10. And we're saying at 1. At is the convention in Mplus language that means fixed at. So 1, and 1 is the number it's fixed at. So Math 7, so I by Math 7 dash Math 10 at 1 is referring to the fact that all of the coefficients for the intercept growth factor are fixed to 1. And we saw that in our formula. So that's with I by. S by Math 7 at 0, Math 8 at 1, Math 9 at 2, and Math 10 at 3 is simply putting into effect the time scores 0, 1, 2, and 3 that we would use for a linear growth model. So that is saying that this path is 0, this is 1, this is 2, and this is 3. So these are growth factors, but they're factors. So we can define them using the by option of the model command. And then what are we saying in the third line? Here we're using square brackets to refer to the intercepts of Math 7, Math 8, Math 9, and Math 10. So as a convention in Mplus, when we use a variable name within brackets, we're referring to either a mean, an intercept, or a threshold. So here these are intercepts because these are dependent variables in the factor model. It's like Math 7 on the factor. So Math 7 through Math 10 refer to the intercepts, and we're fixing them at 0 because that's part of the parameterization of the model. And in a factor model, the means of I and S are fixed to 0. So we have to mention that when we're using the by option. We have to mention I and S, and because they're in brackets, that means we're referring to their means. So we have to mention that to free them. So just to go over it again, so we're specifying the growth model in the model command. We're fixing the paths for the intercept growth factor to 1. We're fixing the paths for the slope growth factor to the time scores for a linear model of 0, 1, 2, and 3. We're fixing the intercepts of Math 7 through Math 10 to 0. And we're freeing the means of the intercept and slope growth factors. So that's just taking all the formulas that we saw earlier and putting them into the Mplus language. Now, the alternative language that you can use is in the model command would be just simply saying IS. That's naming the intercept and slope growth factors, and then giving a bar, and then saying Math 7 at 0, Math 8 at 1, Math 2 at 2, and Math 9 at 2, and Math 10 at 3. And what that does is causes Mplus to do all of the rest of this for you. So we just take the information of the time scores. We fix everything to 1 for I. We fix the intercepts to 0, and we free the 2 growth factor means. So. And in Chapter 16 of the Mplus User's Guide, there's a table under the section on growth models that shows for each growth model, or for many, many growth models, the by language and the bar language, so that you can see with the bar language what you're actually getting. And if you're more comfortable using the by language, it's exactly the same thing. It's just that I found for myself and I found for other people that sometimes, you would forget to fix the intercepts at 0, or, it's a lot to remember if you don't do it all the time, and people made mistakes, so we thought the growth language was simpler. But it doesn't preclude using the by language, if that makes you more comfortable. So now we've specified the model, and you'll see in the output command, I've asked for SAMPStat, which is like asking for basic, but when you're running a model. I've asked for standardized results, and that will give me also R² for each outcome. And I've asked for modification indices. And I've put in parentheses 3.84, which means I don't want to see modification indices smaller than 3.84. And I choose 3.84 because that would, for 1 degree of freedom, would be a significant change in chi-square. So that's an explanation of the input. Let's leave the input there. And let's take a look at some of the results. The first thing that we're going to get in our results section of the output, and this is taken from the output, are tests of model fit. So we give the chi-square test, we give the value, so 22.664 is a chi-square value. The degrees of freedom of for the model, 5. And that makes sense according to what we talked about with how many parameters there are in the model and how many degrees of freedom we would have. So we have 5. And then we have a p-value of 0.0004, which does not indicate that the model fits well. Our CFI and TLI look good. the RMSEA is not bad, and the SRMR is not bad. So we only have 900 case observations. So a person probably wouldn't be able to claim that chi-square is too sensitive. It's not that many observations. But let's take a look at the rest of our results and see what we might decide to do with this model. So it's showing some potential for fit. So let's see what else we see. Well, let's take a look at the modification indices that we get. Okay, and let me explain this output for those of you who aren't familiar with it. So with modification indices, we give the modification index in the first column. We give the expected parameter change. That's if you free the parameter that's fixed, what would the parameter value be estimated as? And it's saying if that parameter, S by mass 7, were free, it would be estimated as 0.185. And then it gives two standardized versions of that. STD, which is standardized by using variances of latent variables, and STDYX, which is standardized using the variances of both latent and observed variables. But I think what people mostly look at is the first column, the drop in the chi-square value that would occur if you freed that parameter. So for every fixed and every parameter constrained to be equal to another parameter in a model, a modification index is estimated. And we label them just by the same way that we label them in the input and that they'll be labeled in the output. So S by mass 7 is the slope growth factor path to mass 7. And so what this says is if we free that, then our chi-square is going to improve by 6.793. And if we do free math 8, it's going to decrease by 14.694 and 9.766 for math 9. So for 1 degree of freedom, the chi-square change would be 3.84. So these are perhaps worthwhile ways of improving model fit. So that's one thing to think about when we look at this. And another thing is to make sure that what you've specified in your model command actually is happening in your results. So the model results come out as follows, and let me explain what the columns are for you. So the first column gives the raw parameter estimate. And the second column gives the standard error of that. And the third column gives the ratio of columns 1 and 2, which is a z value. So this is what you're going to use for free parameters, which we don't have on the screen right now, but which we will. You'll be using that for significance. So you would, for example, for 0.05 compared to 1.96 value. And then we have two standardized coefficients. So here, we're looking at this to confirm it's the way we thought. So intercept growth factor has all of its paths fixed to 1. We can see that the standard errors are 0, and the estimate over standard errors is 0. Sometimes people go, wait, why do you get standardized in STDYX? Well, we standardize those fixed values. They really aren't meaningful, but we print those anyway. And then for your slope growth factor, let's see, does it look right? Yep, we've got 0, 1, 2, and 3. So that was fixed correctly. So we want to verify that because maybe somehow you misspecified something, or maybe we made a mistake, and you want to inform us about that so we can fix it. So then what do we have here? I think let me put both of these up at the same time. Okay, so we said that because I and S are random effects, they're going to each have a mean and a variance. So here we have means for I and S. And for S, if we look in the third column, we see that it's a significant effect. So there is significant significant slope. So the average slope over individuals is 3.105, and that's significantly different from 0. So it's significantly different from no growth. 0 would be no growth. And so it's significantly different from that. So there is some positive growth going on. So the sign's also important. And then now the mean of the intercept growth factor is really not so much of interest. Whether or not there's variability about where people start is of interest, but exactly where they start isn't so interesting. So we don't focus a lot on that parameter. But we do focus on the variances of those two parameters. So we see here that the variance of I is also significant. So that means there's significant variability around that mean where people start in their growth process. So people don't all start in the same place. They don't all come in with the same score at time 1. There's significant variability. And then we look at the variance of the slope, and that's significant too. So that tells us not only don't they start in the same place, they don't grow at the same rate. There's a lot of individual differences there that we want to understand. So the questions that we're going to be thinking about is, well, why? Okay, these kids come in 7th grade. They're really variable in where they start in math. And they're really growing at different rates over 7, 8, 9, and 10. And we want to understand why that's happening. Because obviously we'd like all the kids to be high and grow quickly. So we want to know, why are the ones coming in low growing slowly, and what's happening with them? And we see that we have this positive covariance between the intercept growth factor and the slope growth factor, which indicates that those who start high grow faster and those who start low are growing slower. Now, somebody asked about the R square. Now, we have the R square here for Math 7, 8, 9, and 10. If you ask for standardized in the output command, you're going to get an R square for each dependent variable in the model, both observed and latent. And we'll see that when we add covariates to the model, and we should get R square for the latent variables. So here, these R squares are pretty healthy. And the residual variances are still significant, which would say that the growth model isn't explaining all of the variability in those outcomes. So there might be some change in the model that could explain the outcome development better. So that's our first output and our first model here. So we have our simple linear growth model. It seems to fit pretty well, but our modification indices showed there could be improvement in model fit. We don't want to just do this hastily without proper thought, but we might want to think about freeing a time score. So let's talk about what that means. So, and this is one approach to a nonlinear growth. One option would be to free time scores. We're going to be talking about other options, but we'll talk about this one first. So we're going to need two latent variables to describe nonlinear growth: intercept growth factor and slope growth factor. So let's take a look at a couple of examples. So our outcomes on the y-axis, time on the x, and let's say we have a model that looks like that. It goes up, but then it tapers off. So we have growth, high growth, and then it gets a little bit lower and a little bit lower. Or maybe it grows at a certain rate, and then it gets steeper. And so, that's not linear. You can't capture by a linear model. That's not going to fit the data well. So what you can do is keep the first two time scores 0 and 1, and then just estimate the other two. So they won't be fixed anymore. So we'll be using 2 degrees of freedom if we free those two. So then the degrees of freedom in our model will be 3. So instead of fixing the time scores, you can actually treat them as parameters, as Bengt mentioned earlier, and estimate them. So this is one approach that we can take. Okay, let me put this here. Okay, so we know that the slope growth factor mean is the change in the outcome for a 1-unit change in the time score. So change in y for a 1-unit change in x. When we have nonlinear growth models, actually, let me put the picture back up over here. Whoops. Okay. When we have nonlinear growth models, the time scores should be chosen so that there's a 1-unit change between the time points of substantive interest. I told you that we would perhaps do between 0, the first two, 0, 1, free, free would be an option. But you don't have to do it that way. But what you do have to remember is that the slope refers to the change between the time point that's 0 and the time point that's 1. So it's not, the slope is not constant over time because you don't have a linear growth over time. So the slope is only going to apply to the linear part of the model. So that would be between 0 and 1. Or let's say you had 6 and you had 0, 1, 2, free, free, free. I think that's 6. Then the slope would apply to the fixed part or the linear part of the model, which makes sense. The slope can't apply to the nonlinear part of the model. So let's say you have an example like ours, grades 7, 8, 9, and 10. You could make your time scores 0, 1, free, free. So then the slope factor mean would be referred to changes between 7 and 8. But if you made the time scores 0, free, free, 1, then the slope factor mean is going to refer to the change between 7 and 10. So when you leave the world of the simple linear model, and you free time scores, you may make your model fit better, it may be more meaningful, but your interpretation changes too, so you have to remember that. So the slope growth factor is only going to apply to that. So in this picture, the mean of the slope growth factor is going to be talking about the linear growth here, or in this picture, the linear growth here. It won't refer to the nonlinear parts of the model. But it still is, I think, a flexible tool to be able to have a time score as a parameter. And so, as I said, you have to worry about identifying the model, too. You have to have at least one fixed time score besides the 0. So you have to have at least 0, 1 for the 4 time points. And if you had 3, I'm not sure if you, well, you probably, yeah, you have 1 degree of freedom, but so you could identify 1 free time score. But you have to be concerned with model identification when you start freeing time scores. You just can't, like if you have 16 measurement occasions, you can't just fix 0 and 1 and have the rest be free. And also, that I've seen things like that, and I'm not sure how that would be interpreted. So you need to consider identification of the model and interpretation, which we just talked about, and the approach which we just talked about. So let's take a look at what we might do with our LSAY data. Oh, and a caveat I forgot to mention and that we always try to mention is we do these analyses with real data, but we don't necessarily do them with real substantive knowledge, so I wouldn't discuss our results in a meaningful way. It's for illustrative purposes only. So let's see. Now I've got the alternative language below as by. So the by is down here now. And instead I'm showing you with the growth modeling language how I would free the parameters. So I have math 7 at 0 and math 8 at 1. So I would just take at 1 off of 9 and 10. And that will free those time scores. And we'll be estimating them. So that's the only change you would make to the simple linear growth model to estimate a model with free time scores. And you can see over here that when I did that, the degrees of freedom went down 2, just as I would expect. So I have 3 degrees of freedom. And the chi-square fit increased very well. So by freeing those 2 time scores, the model fit increased very much in all areas. So that's a good thing. And let's take a look and see if it's as expected. So we have our fixed ones here, and we have math 7 fixed at 0 and math 8 at 1. And math 9 and 10, the time scores are estimated. So you can see they're not estimated at 2 and 3 because that wasn't a well-fitting model. Math 9 time score is 2.452, math 10 3.497. Now we don't really want to pay attention to these significant values because they are comparing 2 to 0 or 2.452 to 0. Is 2.452 significant from 0? That's the question that this answers. 17.540 answers the question, is 3.497 different from 0? The question we want to ask is 2.452 different from 2, which we would have fixed it at if it were a linear model? And the answer is gotten by taking the difference between 2 and 2.452 and dividing it by the standard error. And the answer to the question, I think, is still in both cases yes. So these are significant. This is 2.452 is significantly different from 2, and 3.497 is significantly different from 3. So that we would not really want to change that if that weren't the case. And let's see what else happens. The variance and mean of S changes, but we still have a significant variance of S. Because remember now, S only applies to the difference between 7 and 8, not 8 and 9 and 9 and 10 anymore. So we would expect that. But what it tells us is that there's still significant slope. The mean is still significant. It's not flat. And that there's still significant variability in growth just between those 2 time points. Now, I had asked for residuals in the output and in the output command, and this is something you might find useful also for trying to see where your model doesn't fit. We give, in the way we give the residuals is first we give the model estimated values and then the difference between the model estimated and the observed values. So for the means first, and those are quite small, and then for the covariances. And you can see, for example, this is a little bit larger than some of the others, but this is just a good option to ask for, to look at your residual output. Sometimes that can give you an indication of model misfit in addition to the modification indices, although the modification indices are scale-free, whereas the residuals aren't. But given that math 7, 8, 9, and 10 are measured on the same scale, scale-free is really not an issue. Okay, so we're up to covariates in the growth model. I think I need to speed myself along a little bit. All right, so as I said earlier, we want to have a well-fitting growth model, and we want to know if people start out the same and if they grow the same and whatever. But what we ultimately want to know is why. Why do they start out differently, and why do they grow differently? So that's where covariates come in. And I think Ben mentioned this before. There's two types of covariates. Time invariant, so they don't vary over time. Time invariant, they just vary over individuals. And then time varying, which vary over time and individuals. And here's a path diagram that shows you. So for example, here's the growth model that we've been used to looking at. We have our outcomes at the top, intercept and slope growth factors. W is a time invariant covariate. For example, gender. It's only measured at one time point. Time varying covariates, A21, A22, A23, A24. In our math example, with math achievement as the outcome, the time varying covariate could be attitudes toward math. So Mplus can estimate models with one or both types of covariates. So the model that we're going to look at now is the same model we've been looking at on the top here, but we're going to add two time invariant covariates. We're going to add mother's education, and we're going to add home resources to try to understand if either one of those covariates is the reason that people are starting out differently and growing at different rates. And let's take a look on your right screen, no, your left screen, and see what we do to include those covariates in the model command. Well, first of all, we put the variables on the used variables list. So if you aren't using all the variables on the names list in your analysis, then you should put the variables you are using on the used variables list. So we're adding mother's education and home resources to Math 7 through 10. And we use in the model command the on option for regression. So we say IS on mother's education and home resources, and that means on is short for regressed on. So INS are regressed on mother's education and home resources. That's all we have to do to add covariates to the model. Now this example, you'll note that I have an exclamation point here in front of estimator equals MLM. The default estimator for this analysis is ML, maximum likelihood. MLM is a robust maximum likelihood estimator. And what we're doing in this example, in addition to showing you how covariates are added to the model, we're showing you the difference between the two estimators to deduce whether these variables are non-normal or can benefit from a robust estimator. So here's the maximum likelihood results. Don't you dare fall asleep. Okay, so on your left screen, we have the maximum likelihood results as far as tests of model fit go. And you can see that the model fit's not bad at all for this. Chi-square looks pretty good, and everything else does too. But MLM, the robust estimator, which is robust to non-normality, looks even better. And the scaling correction factor, 1.852, is greater than 1, which would indicate that there is non-normality that can be accounted for. So I think our default in most of Mplus is to use actually MLR, we use this because this is the Satora-Bentler chi-square, which many of you are familiar with. We have another estimator that's robust to non-normality that we use as our default that we like a little better. It's called MLR. But so the reason for showing you MLM and ML is to show you that there is a difference when you use the non-normality robust estimator. Now, here I'm showing you the selected estimates for ML on this screen because they're going to be the same, although the chi-square values or the standard errors will be different. I don't think I show, no, I don't show that. All right. So the point of doing this is to understand the relationship between the intercept and slope growth factors with the covariates, mother's education and home resources. So here is some selected estimates from our output. So we have I on mother's education and home resources, S on. And you can see that mother's education and home resources regression coefficients are significant. So that would indicate that mother's education and positive and home resources does affect where students start in grade 7. So their intercept. S on mother's education and home resources, positive coefficient, indicates that mother's education does not have any impact on the growth rate, but home resources does. Now, once again, these are two of many covariates that are probably way more important in an analysis like this. So not to make too much of this, it's an illustration of how you would add covariates to the model and how you would interpret the results when you got them. So, you know, you could be saying, okay, mother's education and home resources, you know, that affects where they start. Interesting finding, something like that. But anyway, this is the point here is that you want to add covariates to understand this. Now, once again, we have our R-square values, which are very healthy for the outcomes, but as you can see, very small for the intercept and slope growth factors. So we have not explained very much of the variability in those intercept and slope growth factors. So there are a whole set of more important covariates out there somewhere. And as Bengt mentioned, it's often hard to find covariates that do explain the variability in these factors. The next 2 pages, or 4 pages, I think, are pretty self-explanatory. The first 2 are formulas. The second 2 are an explication of those formulas. And then we come, should I do centering before lunch, or how should I do this? You know where I am better than I do. Okay, and then what comes after that? Okay. All right, so let's take a look at centering. And so the centering determines the interpretation of the intercept growth factor. So we've been working with the intercept growth factor, the time score fixed at 0 at time 1. So that determines the interpretation of the intercept growth factor. So we've been looking at it as initial status. And we can estimate a model with different centering points. In fact, you could estimate the model and re-estimate the model with the centering point at each time point, one at a time. And when you do that, and then you do the regression of I on, you are seeing whether the covariates explain the mean at that the mean of the intercept scores at that particular time point. So we've been looking at initial status. We could have the time score be 0 at final status, and then we would be explaining final status with the covariates. And once Bengt and I did a paper where we actually did it at every age, and we found that the importance of the covariates changed. For example, dropping out of high school related to alcohol use. Dropping out of high school wasn't very important when you were younger, but that covariate became more important by the time you hit like age 30, which makes sense because you're not dropping out of high school, you know, it just happened, it's not really hurting you too much, but by the time you get that old and you're a high school dropout, you know, it's going to have a much bigger impact on you. So that's what's interesting about centering. And when you change the centering point, and this is always good to know, you should get the exact same model fit because it's just a reparameterization of the model. You're not changing anything but the centering point. So you should use that as a way of checking that you're doing your work correctly. So let's just take a look at the mechanics of this. So if we have our time scales 0, 1, 2, 3, centering at time point 1, all you do to center at time point 2 is subtract 1 from every time score. So then the time scores are -1, 0, 1, and 2. Same thing for 3, same thing for 4. So if we want final status, our time scores are going to be -3, -2, -1, and 0. So it's a mechanical operation. And if you look, what I did is I decided to center at grade 10 in the example that we have. So, and I had free time scores, so I have to take that into account. So the change is the change up here is Math 7 free. An asterisk represents free. At represents fixed at, asterisk free. So this is saying, let's start Math 7. It's a free parameter at -3, Math 8 at -2, Math 9 is fixed to -1, and Math 10 is fixed at 0. So I've just changed the time scores, and that changes the centering. So I've changed the centering from initial status to final status. My test of model fit, I double-checked this. It's exactly the same as it was when it was initial status. So there's no change in model fit. However, we don't see a change in the regression of I on Mother's Education and Home Resources. Both are still significant, even at grade 10. But it is possible that they wouldn't be the same, as I mentioned that Bengt and I saw in a paper that we did many years ago. So this is why you might want to change the centering. And you might have a situation, we don't do this example in these days, but where you have one process, and you might want the ending point to center at final status for the one process, and in the second process, center at the initial status, just to feed into them. So a lot of these things just have to do with what makes substantive sense in your particular model estimation. And then we have a lot of further readings that you might be interested in looking at. I don't know, Bengt, if you have anything you want to say particularly about those references. And then we probably
we could say a few words about them. So here's the Raudenbusch and Bright text that is very popular in the US, at least. If you like more words per formula, you may want to read this book. They do a very careful job in describing models, the rationale for a model before they get into the statistical modeling. And they also talk about survival analysis. Event occurrence is another word for that. So start with either one of these three books. Here, there's a Dutch book here too, although it's in English. Those are very good. And here are our contributions to sort of pedagogy. This is the paper Linda referred to where the centering point changed over time. Here is an effort to be pedagogical in writing about this early on by myself and a student. And here's that Bull and Curran book from Wiley that we talked about. So I think maybe we should take questions and answers now.
Okay.
Next topic is an interesting one, piecewise growth modeling, but we want you to be back fresh for that after lunch.
Yes.
When you decide to free up some time points in iterative effects interpretation, so for practical purposes, is there some kind of theoretical justification that you can present in a paper when you're saying I'm going to free these time points because it does make it more difficult for the reader to understand what you're actually doing?
Wait, I guess I don't read enough papers to know.
Yeah, I think you should definitely have a substantive rationale for it, and as we will see in this case, for LSAY, there's certainly a rationale for both a picture like this, that is math performance tend to level off a little bit towards the end of high school. US children seem to be a little bit tired of math learning at the end of high school. So there's a substantive reason for it. And also there's a substantive reason for an acceleration between grades 8 and 9 because so many more advanced math courses take place. But you should have that kind of rationale for it.
But wouldn't you just be able to actually estimate a quadratic growth model where the parameter is interpretable for each?
Yeah,
We're going to talk about a quadratic model. That's another option.
It would be the same essentially?
Well, the thing about a quadratic model is they're not that easy to interpret either.
But they can be interpreted at each time point. What I may be misunderstanding, it sounds like you can't interpret the coefficient or time points where
You can only say that it's...
well, no, it's not exactly that way. What we tried to stress was that the slope mean, for instance, that parameter refers to the growth between the 0-time score and the 1-time score. But that doesn't imply that you can't interpret the whole development. It's just that the change in the means is the slope mean for that first segment, but then it's a slope mean times the time score, so it becomes more involved. But I don't think it's too hard to interpret. It is the matter of how easy it is to interpret the covariate effects. The covariate effects, as we'll talk about after lunch, it's a little hard to deal with 3-time scores, but also with quadratic growth. And that's why we advocate the piecewise when you can deal with that. Yes?
For slide 92.
9-2?
Yes, 92. So, math 7 and 8, are they fully estimated here?
Math 7 and 8, yeah, they're freely estimated with starting values. So what that's saying is Math 7 is free. The asterisk means free. And I'm giving a starting value of -3. So that's a starting value. So a number that follows an asterisk, which represents free, is a starting value. Yes?
I was using, this is not a linear question, but it's about the less than likelihood and the less one for non-normal data. Had a variable that was severity of sexual abuse, but it included the children who were not sexually abused, which were the vast majority.
Right.
So using it as a continuous variable, it was really non-normal.
Bank is going to be talking about models with preponderance of zeros,
Okay.
which I think that would fall under sometime this afternoon, right?
Yep.
So I think that'll help you.
But in terms of using the robust versus the regular one, does it matter if it's a categorical or a continuous variable that we're using it on?
Well, with categorical variables, we talk about floor and ceiling effects, and what we say on the categorical day is basically if you have a strong floor effect or if you have a strong ceiling effect, so you have a piling up, then you should use estimation method that's specific for categorical outcomes, like our weighted least squares or our maximum likelihood for categorical outcomes. So you wouldn't try to use non-normality robustness to help with a categorical outcome that's got floor and ceiling effects.
How non-normal is okay for?
Well, for categorical outcomes, any floor and ceiling effects, if it's got more at the beginning than the next point, any piling up is going to hurt you for categorical outcomes.
Continue.
For categorical. She was asking categorical.
Yeah,
Well,
well,
actually,
if your
Okay.
outcomes are categorical, the model actually takes into account the piling up.
Right.
There's no violation of assumptions, but if you have a continuous outcome that's piling up, then you're violating the normality assumption, and then it's the two-part or the zero modeling that Linda was referring to that you need to work with.
Right.
But you're asking at what point do you need to switch from non-normality robust to a serious modeling of zeros? That we're going to talk about this afternoon. We're going to show you graphs that tell you that.
So for continuous So just to sort of summarize, so we have categorical variables with piling up at the ends. Those you should use special estimation techniques that can handle that. For continuous with piling up, the models that we talk about this afternoon with a preponderance of zeros would be an appropriate way to go.
You mentioned that you have 16 assessments, for example. You wouldn't advocate using time score of 0, 1, and then let the model estimate. Would it be appropriate to set the first scores to 0 and 1 and then set starting values to a linear parameter?
And then do what? Set it to...
Still free, but set the starting values?
Starting
Oh, starting values. Well, it's sort of like if you're going to do a growth model and you're going to estimate a slope parameter, if it's only going to really be interpretable, I mean, it's sort of like if you have that many free parameters, maybe you should go to a quadratic or a piecewise, because it's sort of like your growth model slope parameter, which is an important parameter, is only talking about such a small part of your outcomes. Do you think that's a valid answer?
Yeah, but you get a very flexible model if you allow the time scores to be free. And you can certainly say 0, free, and then 1. And then the slope mean parameter will refer to the growth from the first to the last. And you're just sort of perfectly fitting the growth curve shape. But I don't know how much you gain by that. I guess I would agree with Linda, if you have that many free time scores, then you might want to switch to a nonlinear model. But it's certainly been, in psychometrics, that kind of almost all time scores free has been explored by people like Meredith and Tysak in their original modeling, and also by Tucker in his papers from the 50s, so it's not unheard of. Yes.
Colorado. Yeah, slide 73.
73?
Yeah, 73. You allow time scores from S10 and S3.
Right.
We are submitting here from 0, but content of level is significant difference from S.
From 2, for example?
Yeah.
Well,
from S8 to S7.
so you're asking, how can we tell if this is significantly different from 2?
That's right, yeah.
Okay, so then you would just take the difference here between 2.452 and 2 and divide it by 0.133.
Okay.
And look at if that's greater than 2, for example.
So this also means the slope is different. Leaf slopes are different from earlier.
You mean because they only apply to 0 and 1?
Yeah.
Yes,
Yeah, so
exactly.
So, we talked about the slope mean, and Linda showed those formulas. So the change from Math 7 to Math 8 is 1 times the estimated slope mean. The change from Math to grade 8 to grade 9 is 2.452 times the slope mean. Not 2, but 2.452. So that's that lambda times the means, the lambda being the factor logam times the slope mean. That is the change in the outcome, the expected change in the outcome. So the model is perfectly interpretable. It's just that once you want to throw in covariates to explain the growth factors, then the meaning of the growth factor has a fairly limited range, right, in this approach. So we're not totally trying to convince you to use free time scores. We're just showing that as one little step towards understanding your data better. Yes?
This is a technical question, but when in this before the sampling the covariate, you show this time invariant covariate. But can you actually explain how to do with time variant covariate?
With the time variant covariate, I don't know if you remember the picture that had that. Do you know what page it's on?
Yeah, that's page 40 and slide 79.
79, okay. So how you would do that is you would add to the model, you would use on statements. Whenever you do regressions, you would do y1 on A21, y2 on A22, y3 on A23, and y4 on A24. So you would just use the on option to add those to your model.
So if I have two two time varying covariate, it could be Y1 on A21 and A31.
Yeah. So exactly. It's very flexible. Dependent variable on the left-hand side of on, and one or more independent variables on the right-hand side of on, as long as the model's identified.
A question in the back there, yeah.
Yeah. What are you using as your general rule of thumb?
I can't hear you.
What are you using for your general rule of thumb for the chi-square model fit? Is it not 0.05 being above 0.05?
Yeah, so give us a page for chi-square.
81, or no, excuse me, 82.
82. Because I think maybe we should elaborate on that a bit. For those of you who are used to ANOVA, you talk about p-value. You want to find small p-values, right? Because then you reject the hypothesis that your experiment has no effect, and you want to reject that. But in this case, we do not want to reject the model. We want high p-values, and the p-value is sort of what's the likelihood that the model is correct. So we want high p-values. Rule of thumb for chi-square, well, we discussed that a lot in day one, but a brief summary would be...
Greater than 0.05.
What?
Greater than 0.05.
Yeah, we want p-values greater than 0.05, basically, but we can live with smaller p-values if the sample size is very large. Probably we can live with them, because then chi-square tends to be a little bit on the sensitive side. And then we would probably want to do an empirical investigation of the alleged oversensitivity by including more parameters to pull down chi-square to increase the p-value, and then ask ourselves, first of all, have the key parameters changed at all? And second of all, are those extra parameters of any meaningful nature? And if the key parameters haven't changed and the extra parameters are not meaningful in nature, well, then you have demonstrated empirically that chi-square was too sensitive. Therefore, you could live with that smaller p-value.
So you could get away with this.
You could get away with this, but whenever you have this situation, you may want to do further modifications on the model and see